Hello, this is Miraj Patel, and today we're going to be talking about VSPER models of covalently bonded molecules, and then we're going to be talking about polar versus nonpolar molecules. And so first, we have a PowerPoint about valence shell electron pair repulsion theory diagrams, so VSPER diagrams. And so pretty much the VSPER says that electrons spread out in different shapes to minimize repulsions. So if you just think about like electrons or any magnets, the negatives don't want to be next to each other. So pretty much the shape is all based off of how these electrons want to repel each other. And so how does a molecular formula get its shape? And so pretty much assume that all electron pairs are spread out and then predict its shape. And so pretty much we have to first draw the Lewis dot structures like we've been doing, and from looking at these electrons and where they are located, you can predict its shape and tell exactly how it will look like, or most hopefully look like. And then again we have these non-bonding pairs or lone pairs, and we have the bonded pairs, and we'll talk more about exactly how to find the shape. And so there's this thing called electron domains, where all single, double, or triple bonds pretty much around the central atom count as one domain. And so electron domains are pretty much areas where there's electrons, and so all bonds, whether they're single, double, or triple, count as one electron domain. So from this, you can say how many electron domains are there around central atom A, and you can count 1, 2, and 3. And so there's 3 domains because each bond counts as 1. So one bond here, one double bond, so it's still one domain, and then a second domain here, so 3 total. And so here's like a general like a formula about electron domains. So pretty much it says A, which represents the central atom, and then B, I like to represent it by saying bonds. So just think of, so there's one central atom and then B, so there's 3 bonds. We write a little subscript called 3, and this 3 represents the 3 different electron domains. And then we have another example. Each lone pair of electrons counts as one domain, so each bond counts as one domain, and then each pair counts as one domain. So on this atom, how many domains are there around central atom A? So there's 1 bond here, 2 bonds here, 3 bonds, and then there's 1 lone pair, so there's a total of 4 electron domains around atom A. And we would write it like this. So we have A, the central atom, B represents bonds, but we have 3 bonds, and then we have a separate variable, E, for lone pair. So E represents this lone pair, and there's only 1, so there's an assumed 1 here. And so total there's 4 domains, and you can count 3 B's, because it's a little subscript, and then 1 E, because there's an assumed 1 here. And then so after we get the general formula, we can predict its shape. And so here we're going to go over all the shapes. So we have A, B, 2, so A is the central atom, like this, and B represents the bonds, and so, or the number of atoms it's bonded to. So there's 1 bond here and 1 bond here. So there's 2 bonds total, so only 2 electron domains. And so pretty much it forms a straight line, and so from geometry, a line has 180 degrees around the central atom, or like the vertex. So just think of this as just a line, and this an example of a linear compound is CO2, and so you can see how the carbon is in the center, and it forms a straight line with these 2 oxygens because of how they bonded, and their electrons, the domains. And then we have the second shape, which is trigonal planar. And so here we have a general formula of A, so one central atom and then three atoms, bonds around it, and there's nothing else. So the bond angle is 120, and if you did not know this, you could figure out by just imagining this as a circle. So circle we know has 360 degrees, and so if we have three lines separating a circle, each section would have 120 degrees because 360 divided by 3 is 120, or 36 divided by 3 is 12, but just add a 0. And so there's a bond angle of 120, and an example of this is boron trifluoride. So here we have one boron molecule, and we have three fluorine, and it just makes a trigonal planar shape because it has three bonds and then one central atom. And then we have three more shapes, and so here we have AB4, so one central atom and four atoms or electron domains around it that are in the form of bonds. And this is called a tetrahedral shape, and a bond angle, which is weird, it's not like 90 like the other one. So normally if you divided a circle's degrees by 4 you would get 90, but this one's weird because we have a 3D angle. So notice how it's not a right angle, it goes slightly more down. So the angle is weird, but it's 109.5, and an example of this is carbon CH4, and here we have one carbon molecule, and then we have these four hydrogens, and so the general format is AB4, and just for your information, these lines they just represent bonds, but this line represents a bond that's an atom that's coming at you. So notice how this B is coming at us, and so that's the same thing with this, and then this dotted line represents that it's going back into the atom. So it would normally be going away from us, and then this one be coming towards us, and this just represents this normal bond. And then we have NH3, which is a AB3E atom or molecule, and so we have one central atom, three bonds, but then we have a lone pair, which is represented by the E, and this is called a trigonal pyramidal shape, and it looks like this. So pretty much it looks like a pyramid, and the reason why it's not trigonal planar is because of this lone pair that sort of repels all these electrons, and that's how electron repulsion is included in the VSPER models, because we're assuming that these electrons are pushing away. So this lone pair is pushing all these, and that's what's causing it to bend downwards. And then we have the last shape, which is the bent shaped, which has one bond, two bonds, and then two lone pairs around the central atom. And it's called a bent shaped, and a good example is water. So again, this dotted line just means the bond is going away from us into the background, and this one means it's coming towards us. And so pretty much these lone pairs push the atoms, or push the other atoms bonded to get on this away from the center. So normally if we took away this E, it would look straight, linear shape, but we have these E's that push these atoms away. And so here's again a brief summary. So we have AB2, which is a linear shape, 180 degrees. And then we have AB3, so think it looks sort of like a triangle-ish. And so it has 120 degrees around, and it's called trigonal planar. So think of tri, so 3, and then trigonal, which sounds like triangle, and then planar just means it's on the same plane. Then we have tetrahedral, and tetra is 4, and then so that's a good way to remember that. So four bonds. And then we have trigonal pyramidal, so think of tri again, but pyramid, so think of it as a 3D shape. And then we have a bent structure, just think of like a bent paper clip. So you just bend it, and it just makes like an upside down V. And again, the angles are 180. then 120, and then 109.5, the weird one that you have to memorize. But that's the only one you have to memorize. These two you can figure out just by the shape. And then here's how you predict the geometry. So there's 3 easy steps. So first, we have to draw the Lewis dot structure. So hopefully you know how to do that. And if you don't, just refer back to the last video. And so here's the Lewis dot structure. And again, follow all your simple rules like keep track of the electrons, bond all the atoms. Then if you don't, just remember to double up and stuff like that. Then we have to count the electron domain. So remember, each bond is one domain, and then each lone pair is one domain. So we have 1, 2, 3, 4 domains, and it would be written like this: AB, not 4, but AB 3, because we have 3 bonds, and then 1 pair of electrons, which is represented by the E. And then we can name the shape. So based off of this little mini formula, or domain formula I like to call it, we can tell its shape. And so if you just imagine it, if you're like a visual learner like I am, you can just imagine this pair of electrons sort of pushing down all these atoms. And if you don't remember this, or if you don't think of it as visually, you can just always go back to the page with all your formulas and just compare the little formula with the shape. And so it was AB3E, so it had to be trigonal pyramidal because this E sort of pushes all these down. And so that would be the correct shape because it's not tetrahedral, it's pyramidal because this little bond, these two lone pairs push down everything. And so here's a quick quiz to see what you learned. So what is the molecular geometry of pH3? And then so it's linear, trigonal, planar, tetrahedral, or trigonal pyramidal. So if we do the Lewis dot structure, so we have all the bonds and we check it all. So we have this one lone pair, and so if we do the little domain formula, we have A for central atom, 3 bonds, so B to the subscript 3, and then we have E for one lone pair. So we have A, B, 3, E. So if you just imagine these electrons as pushing these hydrogens down, we would have a pyramid shape. And so which one contains 3 bonds and has a pyramid shape? So the answer would be D, because if you just think about trigonal, so tri, so 3 atoms, or 3 molecules bonded, atoms bonded, sorry. And then we think of pyramidal, so as a pyramid, so these things, this pair pushes these electrons down, or, atoms down. Then we have the next question: which molecule has a trigonal planar geometry? And so, let me just show you the answer, and then we'll just go through each of the. So let me just show you all the answer, and then we can go through all these shapes. So if you drew the correct Lewis dot structures, you should have no problem. And so for this first one, we see that we have 3 bonds and 1 lone pair, so it's AB3E. And then again, E, this lone pair, pushes all the atoms down. So this would be a trigonal pyramidal shape, sorry about that. And then we have H2O. So we have 2 lone pairs and 2 bonds. So it's AB2E2. And these 2 lone pairs push these atoms away, and it creates an upside down V, or bent shaped. And then we have this last atom, so it's carbon in the center with the 3 hydrogens and 1 fluorine bonded to it. So we have 4 bonds, so it's AB4, and then so this is a tetrahedral shape. And so then we have the last compound, and so we have BH3, so we have 3 hydrogens bonded to this 1 boron. And the weird thing about boron is it only needs 3 bonds to be satisfied, so that's why it does not have a lone pair, and so that pretty much just forms a trigonal planar shape. And so that is it for this part. And so now we're going to be talking about polar molecules and their bonds. And so here we have a chart that categorizes bonding. So bonding is divided into ionic and covalent bonding. So ionic bonding is pretty much, if you have to describe it in one sentence, it's pretty much bonding by the transferring of electrons. So in ionic bonding, the electrons are not really shared equally. They're like always pulled to one side or the other. It's never in the middle. And then covalent bonding is pretty much bonding by the sharing of electrons, so they're somewhat shared, so they have to be contact by both. But ionic, they're either to one atom or to the other, they're never to both. But covalent is also split into two categories, which is polar and nonpolar. And so just by looking at this word, polar and nonpolar, you can sort of just think about the Earth. So we're gonna just stop talking about chemistry for a second. Think about the Earth or magnets. So if you know, the Earth and magnets both have like a north or positive and south or negative end. So so polar, or like the North Pole and South Pole, each have their own separate charges. And so pretty much that's why like the magnets work on Earth, because Earth has slightly positive and negative charge, so it's pretty much like a big magnet and has a big magnetic field. And same thing with magnets. So if you think about the two poles of a magnet, they have different charges. And then non-polar is exactly what you think. So non is not, and then polar is, just like we talked about, has two different charges. So non-polar is no two different charges. And so here's another analogy. So we have a non-polar covalent bond. And so pretty much these electrons are shared equally, just like in this tug-of-war scenario. These people are pulling equally. So pretty much that this rope isn't moving anywhere because both sides appear right now to be pulling with the same amount of force. And same thing in nonpolar covalent bonds. These electrons are shared equally by the two different atoms. And here's another diagram showing pretty much the same thing, but in the molecular scale. So nonpolar atoms are atoms with equal pull or similar electronegativity, so the bonding electrons are shared equally. So here you can see that there's a nice oval around the electron cloud, and neither side appears to have more of the cloud. And so an example of nonpolar elements are like diatomic elements, because if you have the same element, therefore you have the same electronegativity. So both these atoms, like two hydrogens, pull on the same exact force on the same electron. So if they pull with the same amount of force, that means there will be no change in the electrons, so they'll stay in the middle. Same thing with like the tug of war. If we pull with the same amount of force, so if you pull 100 pounds of force one way, 100 pounds the other way, the two forces will just cancel out because they're the same exact force, and the electrons will be left in the middle. But then we come to polar covalent bonds, which are bonding of electrons that are shared unequally. So the last one, nonpolar, is equal, but polar is unequal. So just think about magnets. One has slightly positive and negative charges, and same thing with Earth. So you know how think of the North Pole as slightly positive, South Pole as slightly negative. And same thing with polar bonds. So we have a slightly negative and positive charges on the atom because these electrons aren't shared equally. So here we have HCl, or hydrochloric acid. So we have hydrogen here and chlorine here. And hydrogen has a weaker pull, has a less electronegativity, that's what this means, than chlorine, which has a greater electronegativity. So if it has a greater, electronegativity. So if it has a greater electronegativity, you want to pull on those electrons stronger with more force, and so that's why the electrons crowd around it more than the less electronegative atom. So which is represented by the blue region, which represents the cloud. And so this symbol just means partial, so partial positive and partial negative charges, which are created by the unequal pulling of these electrons. And this is called a dipole, a molecule with two poles. And so cause this causes slightly negative and slightly positive end, just like how Earth has. And here's a chart showing the difference in electronegativity in the most probable type of bond. So if it has a least difference, so 0 to zero point 0.4 difference in electronegativity, it's nonpolar. And then if we have a slightly greater difference, we have 0.4 to 1 difference, then it's moderately polar. And then if we have a 1 to 2 difference, then it's very polar. And then if it's greater than 2, it's ionic. So that means it's not even shared at all. And so here's some examples like H and H. So we talked about how diatomic elements, if you're pulling with the same amount of force, there's no difference. So H is the same as H. So if they're pulling with the same force, the electrons just stay in the middle. Then if we have H with Cl, H and Cl are slightly different. So it's polar because Cl pulls stronger than hydrogen. And then we have very polar, which is H and F, because F is so electronegative that it's pulling so much harder than hydrogen is, so the electrons move towards it. And hence, the more electronegative the atom is than the other one, the negative, it will be negative. So notice how these are negative because they pull the electrons towards it itself. And then we have NaCl, which is from the last unit, so ionic bonds. So if you need a review for ionic bonds, just go back to the last unit. And so electronegativity, there's special periodic tables that tell you electronegativity. And for example, fluorine is the highest electronegativity and it's electronegativity of 4 on most electronegativity of any element. And CH, here's an example. So we have carbon and hydrogen, and so is nonpolar because if you subtract the two electronegativities, which will be given to you on a test, if we have a question, it'll be given to you, the two electronegativities. You just pretty much just subtract them, subtract the smaller one from the larger one, and whatever that number is, you can compare it on this chart. And so if you have 0.4, it's in this range, so it's nonpolar. And so here's the summary. So ionic, or electrons are transferred, so neither one side gets electrons and the other side doesn't. So pretty much think of like people hogging something. So one side gets it all, the other side doesn't. Polar covalence, electrons are shared unequally, but they're not like total hogging like ionic. So we do have an unequal sharing, but one side still gets a little bit. And so nonpolar covalent bonds are shared equally. So both sides share it equally, so neither side has more negative or more positive. And the thing about this one is it's partially positive, partially negative, but this one in ionic, it's either positive or negative, no buts or about it. And so here's last review. So polar molecules have polar bonds, and they're arranged asymmetrically. So pretty much these two polar bonds do not cancel out. So if the polar bonds do not cancel out, so if one goes to the left and one goes to the right, they cancel out. But in this one, the polar bonds do not cancel out because this one goes the same direction as this one. They both go to the top here. And so we have a polar molecule because the electrons are closer to one element than the others. And it's important to know the shape matters. So if the bonds did cancel out, so like one went to the left while one went to the right, it would be nonpolar. Because if you think about it, if you pull 100 newtons of force one way and 100 newtons one way, it just cancels out, so you don't go anywhere. And examples are like H2O, HCl, CH3Cl, and H3. And here are some more polar molecules. And notice how one element is pulling the electrons towards itself. And so all of these, and no bonds cancel out. So in nitrogen, all of them are coming towards it, so they all go to the center. Chlorine, there's nothing pulling it down, so they all go straight up to it. And then same thing in this one, chlorine's pulling all the electrons towards itself. And then we have nonpolar bonds, which have no polar bonds or the polar bonds are arranged symmetrically so they do cancel out. So here's a good example, CO2. So you have carbon and oxygen, but oxygen is so much more electronegative that these oxygens are pulling so much harder on the electrons than carbon is. So we do have two polar dipoles, but they're both they're exactly opposite. So one pulls to the left while one pulls to the right. So just like that analogy, if you're pulling 100 force this way and 100 force this way, they will cancel out. And same thing with this example, CO2 is nonpolar because these two oxygens' forces cancel out. And then we have nonpolar bonds like chlorine pulling on itself. So pretty much if something pulls with the same force as itself, that means it's nonpolar because there's no movement in electrons in the first place. And again, shape does matter. So if it does cancel out, then it's nonpolar. If it doesn't cancel out, so for example, if both oxygens were pulling one way, that means then it'll be polar. But in this example, in the real world, or at least on Earth, oxygen pulls on opposite sides of carbon and CO2. And so here's some more non-polar molecules. Sorry, non-polar, but these are polar bonds. So in non-polar molecules, there can still be polar bonds, but as long as they cancel out. So here, look how it's symmetrical, and all the bonds pull out. It can be non-polar. And again, here it looks symmetrical. This chlorine pulls this way, this one pulls that way, the other one pulls opposite. This one also pulls opposite. So all these cancel out. And so here's a quick quiz to see what you learned. 1. In a nonpolar covalent bond, electrons are blank. A. Gained by one atom. B. Shared unequally between atoms. C. Shared equally between atoms. Or D. Lost by both atoms. So nonpolar, which I remind you is no poles, so no slightly positive or negative. So if we have no change in like the charges, so neither side is pulling harder than the other, so they are shared equally. So just think of equally sharing nice like friends. So both friends share equally the same thing. So they're friendly, and so there's no positive or negative differences. So pretty much just think of two good friends. So nonpolar is just like two good friends that share things equally, and they're nice and happy. And so here's another question. Give two examples of nonpolar molecules. So an easy one is just list the diatomic elements, so those lucky 7 elements. Or you can list like compounds like CO2 or carbon tetrachloride, where even though there's polar bonds, all of them pull in exact opposites, so they cancel out. And then here's question 2. In a molecule, the most electronegative atom, A, repels electrons more strongly and acquires a partial negative charge. B, repels electrons more strongly and acquires a partial positive charge. C, attracts electrons more strongly and acquires a partial positive charge. Or D, attracts electrons more strongly and acquires a partial negative charge. So if we have a electronegative atom, I remind you that the definition of electronegative is atoms that want to steal an electron. So atoms that put the most energy on other electrons and can easily steal them. So if an atom is pulling so hard on an electron that it steals it or has a higher electronegativity, it definitely attracts electrons. So you can eliminate A and B because they say they repel electrons, electronegative atoms. And if you think about it, if you gain a negative particle, you become more negative. So if you think about a pessimist that becomes more pessimistic, they become more and more negative. So if you attract an electron, same thing, you attract a negative particle, so it becomes more negative, so it acquires a partial negative charge. So only answer that does that between C and D is D. So that's the correct answer. So pretty much think of how polar molecules have a slightly positive and negative charge because of the electronegative atom that pulls on the electrons. And so, which of the following bonds is the most polar? Well, if you're doing this question, you can't really tell which one's the most polar unless you have a periodic table that tells you electronegativity of each individual element. And so, but right away, let's just look at D. And so, once you see D, you can immediately eliminate that it's the most polar because this is non-polar. Because chlorine and chlorine both pull with the same force. So, if you pull with the same force, or if you're like two friends that are exactly the same and like share equally, they're both happy and they both share the electrons. But if you're like two mean friends, or I don't know, two mean enemies, they don't pull the electrons. So one is slightly happier or positive, and then the other one is all upset and all mean and stuff. So, so just think of these bonds as like two friends sharing something. So if the two friends don't share something, someone's happy and someone's sad. Or if they do share, then they're both equally satisfied. And so immediately you can tell just by seeing chlorine, so two of the same element is pulling on the same force, that it's definitely nonpolar. So it can't be the most polar. And so the answer is HF. And you have to know the electronegativity, and you just pretty much subtract the differences, and the greatest difference is the most polar. And so here we have another question. So why is carbon tetrachloride CCl4 a nonpolar molecule even though it contains four polar bonds? And so A, the polar bonds are too weak. B, the polar bonds cancel in opposite directions. C, carbon is always nonpolar. Or D, carbon tetrachloride has single bonds. So, you know how we talked about how shape is important for bonds, covalent bonds, whether they're polar or nonpolar. So if they do cancel out, so like if one goes left, one goes right, or if all of them go equally in all the different directions, then it becomes nonpolar. And so this is the same thing with carbon. Carbon has no exception. So pretty much the polar bonds, so one goes up, one goes down, one goes left, one goes right. That's the simplest way you can think about it. So all these bonds cancel because they all go in opposite directions. So just think about like tug of war. They're pulling with equal force. And so one side pulls this way, one side pulls that way. And so they're, even though they want to be polar, it's nonpolar because they're both pulling with equal force. And then which of the following is a polar molecule? So if you draw the atomic structures of all these atoms, you can figure out whether they're polar or nonpolar. So first let's just go to the answers and let's just talk about all their shapes. So we have I2, and just by, I bet you are now tired of me saying that diatomic elements, because they pull equally, are nonpolar. So just remember, diatomic elements, because they're the same exact element pulling on itself, they're nonpolar because they have the same force. And then carbon dioxide, we saw, is an example of a nonpolar molecule because the carbon is pulled equally by the both oxygens. And then we have H2S, which is polar, because here we have a diagram. So we have S, H, H. And so the sulfur is way more electronegative than these two hydrogens, so it definitely pulls much harder on hydrogen's electrons than hydrogens do on itself. So it's polar, and there's a net dipole of moving upwards. And then we have nitrogen, which is pulling three hydrogens, and this nitrogen's again so much more electronegative that it pulls these electrons inwards. And just for your information, if you ever do Lewis dot structures, which you're supposed to when you're figuring out whether they're polar or nonpolar, if you see a lone pair on the central atom, so for example, if you see a bent shape, which has two lone pairs, or if you see a trigonal pyramidal shape, which has one lone pair here, it's automatically polar. So if you see a E in the electron domain formula, that means it's automatically polar. So once you see that you have two lone pairs or one lone pair in the central atom, it's polar, definitely. Whether the bonds are are poling or not, just know, just jump straight that it's polar. And so here we're just going to go through all these molecules, and I'm just going to quickly try to explain them in simple terms. So we have Cl and Cl again. Diatomic elements are always nonpolar because they're pulling on themselves with the same amount of force. So this is definitely nonpolar. Here we have HCl, so hydrochloric acid, and you can definitely see this dipole pulling towards the chlorine, so this is definitely polar. And sorry about that. And so here we have oxygen, carbon, oxygen. So these two oxygens, even though these are polar bonds, they pull in opposite directions, so they cancel out. So AB2. So it's definitely nonpolar. Then we have AB3, so three fluorine atoms pulling a boron atom in opposite directions with equal force, so this is nonpolar also. Then we have AB4 and carbon tetrachloride, and so we have four chlorines pulling in opposite directions, one up, one down, one left, one right. And so this is definitely nonpolar because all these cancel out. And then we have another tetrahedral, but this one, the chlorine is so much more electronegative, which you can figure out from looking at the periodic table, than the carbon, that it's pulling much stronger on these electrons. So it's polar, definitely, because chlorine is so much more electronegative, and you can tell by this dipole. And then we have these two molecules which have a lone pair. So if you see this E, they're definitely polar, and it does work, in fact, because we have water with two lone pairs here, and so this oxygen is pulling on those electrons, and even the hydrogen's electrons, harder than the hydrogens are, so there's definitely polar. And then we have nitrogen pulling on three hydrogens, and then there's also a lone pair because of this E, and it's definitely polar. And so, a brief summary of what we've learned. We've learned how to draw VSPER diagrams based off of the Lewis-dot structures and lone pairs. And so pretty much, if we have in a compound, we have to first draw the Lewis-dot structure and find the little the electron domains and write it in that notation like AB2, E2. And so based off of those little domain formulas, you can figure out the shape by looking at the chart, or you can just visualize it in your head. So just think about each atom repelling equally. And then we have polar and nonpolar molecules. Polar molecules share it unequally, so think about two like people that don't like each other, so they don't share like their ice cream or food equally. So one hogs it while the other one gets a little bit. And so just don't get confused with ionic. So polar is just like sharing unequally. So think big brother and little brother. They don't really like each other. So one guy gets like a quarter of the cookie while the other guy gets 3/4. So that's not equal. So and then polar molecule or non-polar molecules are share them equally. So think about like a two good like sisters, and so how they share their cookies equally. So each sister gets one half of a cookie. And so again, polar molecules, they're they have polar bonds in them, and they don't cancel out. But if they do cancel out, they'll be nonpolar, because if one pulls left, one pulls right, those two bonds would cancel out. If one pulls up, one pulls down, those would also cancel out. And also remember to draw the Lewis-dot structures and figure out the shape based off of the VSPER diagrams, and sort of like combining those two. And then if you see lone pairs, always remember it's always polar. Always polar. And so I hope that helped you learn about the VSPER diagrams and whether molecules are polar or nonpolar. The next video we'll be talking about how to name these compounds. So like how we get the name carbon tetrachloride or carbon dioxide. And then so we'll see you later, and I hope you have a good day.